Scientists at Cern have made a discovery that is revolutionizing physics and astronomy. Using the Large Hadron Collider, the world's most powerful particle accelerator, the team achieved collisions at an unprecedented 13.6 tera-electron volts and has opened up an interdimensional portal. This marks a new era of exploration, changing our understanding of the universe. Join us as we explore 20 facts about CERN and the groundbreaking discoveries made possible by the Large Hadron Collider. Number 20. CERN and the LHC. Hidden nearly 100 meters underground near Geneva, Switzerland, lies one of the most advanced and extraordinary technological marvels the world has ever seen. The Large Hadron Collider LHC at the European Organization for Nuclear Research CERN. This massive particle accelerator forms a 27-kilometer ring that crosses the border between France and Switzerland and contains a circular tunnel where beams of energy are sent racing around at nearly the speed of light. The LHC makes a constant buzzing and humming sound, almost like a giant scientific playground where amazing discoveries are made on a regular basis. It is not simply an ordinary machine. The LHC pushes the boundaries of technology further than any other modern-day invention. It has taken immense collaboration, planning, and precision to construct the LHC, with over 10,000 scientists, billions of dollars, and engineers from 100 countries working together over 2 decades to make this facility a reality. The LHC is the latest in a series of ever larger particle accelerators probing the building blocks of matter with increasing power. First came earlier colliders like the Tevatron and LEP. Now scientists at CERN play with cosmic fire. The purpose behind this monumental undertaking is to recreate the conditions that existed in the moments immediately following the Big Bang, that massive explosion that created our entire universe. By accelerating protons to tremendous energies of 7 trillion electron volts and causing them to collide, temperatures are generated that are 100,000 times greater than at the core of the Sun. This allows physicists to observe phenomena at the subatomic level, which provides insight into particle physics and the Standard Model, uncovering evidence of new realms of physics beyond what is currently known. Number 19. Higgs boson. The construction of LHC involved thousands of magnets, cryogenic systems, vacuum chambers, and detectors. The superconducting electromagnets contain 1,232 dipole magnets, 15 meters in length, that steer 2 beams containing protons in opposite directions. These magnets operate at -271 degrees Celsius and generate magnetic fields over 100,000 times stronger than the Earth's. The magnets are cooled to operating temperature using over 80 tons of liquid helium, making the LHC the largest cryogenic facility ever built. The beam pipes are kept at an ultra-high vacuum to avoid collisions before the crossing points. The pressure inside is 10 trillion times lower than normal atmospheric pressure. A worldwide computing grid processes over 25 petabytes of data annually from the collisions. In 2012, the Atlas and CMS collaborations at the LHC announced the observation of the Higgs boson, often referred to as the God particle, fulfilling a 50-year search. This elusive subatomic particle is responsible for giving mass to all other fundamental particles, allowing matter to coalesce and exist in the universe. Without the Higgs mechanism, particles would have no substance and our reality would be utterly different. Locating the Higgs was the final missing piece in the Standard Model of particle physics, capping a half-century of theorizing and experimentation. Peter Higgs and others first proposed the existence of this field and associated particles in 1964 to explain how fundamental particles acquire mass. That theory went unproven for nearly 50 years, with particle accelerators unable to achieve the energies required to detect it. Finally, in 2012, the powerful collisions within the LHC were energetic enough to produce discernible traces of the Higgs boson. Its observation was a watershed moment in physics, confirming a long-standing theory about the origins of mass. Number 18. Portal to parallel universe. According to some theories, our universe could be part of a larger multiverse with parallel universes. The math behind string theory and inflationary cosmology allows for scenarios where Big Bangs create bubble universes with different parameters. There could be infinite alternate realities beyond our cosmos, sometimes interacting via quantum effects. So theoretically, extra dimensions could exist beyond the normal 3 spatial dimensions. Particle accelerators like the Large Hadron Collider can concentrate enough energy to briefly interact with those extra dimensions. By colliding particles near light speed, the LHC might manifest hypothetical particles briefly. The LHC is designed to operate at 99.9999991% of the speed of light. On July 2022, Cern attempted its biggest experiment, thunderously crashing trillions of protons at almost the speed of light. The moment the particles raced around the LHC ring at 11,000 times per second, reports started flooding in that something had gone wrong. A strange, unexplained energy was allegedly released from the Cern perimeter, altering the space-time fabric and making the impossible possible by opening up a portal. This incident is now called the Portal Incident. As a result, for 14 hours, the crucial geomagnetic field protecting us from solar radiation was weakened. Solar wind passed through a gap torn open by Cern, fluctuating the global electric grid. Also, the worldwide LHC computing grid was impacted, which provides data storage for over 500,000 CPUs in 200 computer centers globally. Earth's geomagnetic field supports life by shielding us from threats. While the incident was short and grids returned to normal quickly, no one knew exactly what happened during Cern's experiment. Number 17. New physics. While the Higgs boson discovery was a crowning achievement, the LHC was not built simply to find one particle. Its overarching mission is to search for new physics beyond the current standard model that could revolutionize our understanding of the universe. According to supersymmetry theory, every known particle has a heavier partner particle. Observing these helps explain mysteries like dark matter and the hypothesized grand unification of forces. Some theories based on string theory predict the existence of additional spatial dimensions beyond the normal 3 dimensions of space. The effects of extra dimensions could be detected in the LHC's high-energy collisions. Dark matter makes up over 80% of all matter in the universe, yet we cannot directly observe it. The LHC searches for theoretical dark matter candidates like weakly interacting massive particles, or WIMPs. Grand unified theories aim to unify the electromagnetic, weak, and strong nuclear forces into one yet undiscovered quantum force that may have governed the infant universe. Other particles being searched for are magnetic monopoles and strange quarks that could combine into hypothetical strangelets with unexpected properties at the LHC's extremely high collision energies. Number 16. Experimental anomalies. While the LHC has made great progress in illuminating physics phenomena beyond previous limits, it has also uncovered deviations and anomalies that do not fit neatly within the standard model. Such perplexing results serve as fertile ground for developing new theories and indicate cracks in the accuracy of the standard model. The decay of the Higgs boson into 2 photons occurs at a rate significantly different than the standard model prediction. This suggests undiscovered particles and forces are influencing the process. Flavor-changing neutral current decays of B mesons occur at different rates than expected, challenging predictions. This could point to new physics. Precise measurements of D meson decays exhibit unaccounted for CP violation. This may be tied to the dominance of matter over antimatter in our universe. The magnetic moment of the muon is found to deviate from theoretical values. Interactions beyond the standard model could cause such shifts from known physics. Perplexing patterns in neutrino oscillations recorded at LHCb seem incompatible with our current understanding, requiring new physics to explain them. Each anomaly probes the limits of validity of accepted physics from different angles. While experimental uncertainties are still being ruled out, persistent discrepancies represent opportunities to search for new particles and forces. Number 15. Connections to quantum gravity theories. The standard model of particle physics, while remarkably successful, is known to be incomplete because it does not incorporate gravity. Unifying quantum mechanics with general relativity into a theory of quantum gravity remains physics' greatest unsolved puzzle. The LHC could provide clues by testing predictions from different approaches to quantum gravity. According to string theory, elementary particles are not point-like, but actually tiny, vibrating loops of string. The vibrations determine particle properties. Importantly, string theory requires extra spatial dimensions. At LHC energies, particles could briefly interact with these dimensions. Any deviations in behavior could be detected. The existence of extra dimensions is sometimes modeled by quantum black holes. If found at the LHC, these microscopic black holes would evaporate instantaneously in a burst of Hawking radiation that could confirm this quantum gravity theory. Additionally, models with extra dimensions predict modified gravitational forces at small distances. Careful measurements during collisions could uncover this. Loop quantum gravity is another approach that models space-time as a mesh of discrete points. This means there is a minimum distance, and particles display quantum jitteriness. Precision LHC observations may find evidence for such granular jitteriness that emerges at incredibly tiny scales. While a complete theory of quantum gravity remains elusive, the LHC provides an avenue to test predictions from different candidate theories. Number 14. Probing the limits of quantum mechanics. The LHC pushes the boundaries of quantum mechanics into new uncharted territory. Quantum principles like entanglement, superposition, and wave-particle duality mystify our intuition yet underpin the behavior of matter and energy at the smallest scales. By examining these concepts under exotic conditions never before realized on Earth, clues of new physics could emerge. A cornerstone of quantum theory is entanglement, where particle states maintain a connection even when separated by large distances. This non-local effect has been demonstrated over kilometers. Performing entanglement experiments with particles produced in LHC collisions could test this effect further and reveal new insights. For instance, if the entanglement effect appears weaker than expected, or the connection severs quicker, it suggests entanglement may involve extra hidden dimensions beyond our normal 3D space. Any crack in quantum theory emerging from LHC data will trigger a revolution in our understanding. The iconic quantum feature is wave-particle duality, where matter and energy exhibit characteristics of both particles and waves. The intense energies generated in LHC collisions produce conditions where the wave-like aspect of matter dominates. Observing how quantum particle waves scatter, diffract, interfere, and become coherent from the immense electromagnetic fields during collisions could uncover completely new quantum effects. Deviations from established quantum wave behavior would shake the foundations of quantum physics. Number 13. Violations of sacred physics laws. Conservation of energy, momentum, and other quantities are considered sacred laws of physics grounded in massive experimental validation. Incredibly, the recent LHC results and measurements have provided tentative hints that even these most robust laws might exhibit violations under extreme conditions. While major uncertainties remain, the data aligns with some theoretical predictions. For instance, during high-energy proton collisions, fleeting microscopic black holes or exotic particles could momentarily jump into unseen curled-up extra dimensions before returning to our normal 3D world a moment later. From our limited perspective, this could make it appear as if some energy and momentum vanished, violating conservation. The recurring appearance of this missing energy and momentum in LHC data fits what some theories anticipate when extra dimensions are involved. This raises the momentous prospect that we are witnessing our first glimpse into a grander multidimensional reality that surrounds us. Definitive violation of energy and momentum conservation would mean a radical overhaul of physics. Of course, more prosaic explanations like undetected particles carrying away energy cannot yet be excluded. But the chance to push conservation laws to their limits and watch them potentially break down is an electrifying opportunity that the LHC provides. Number 12. Theory of everything. Physicists have long dreamed of finding a single overarching theory that fully integrates gravity with the rest of physics' quantum framework. This theory of everything would unify all fundamental particles and forces, the cosmos's disparate strands, into a single coherent picture. However, formidable challenges confront the development of such a theory. At immense scales, gravity follows Einstein's elegant general relativity, curving space-time like a massive object sitting on a stretched fabric. But at tiny subatomic scales, attempts to force gravity into quantum theory cause absurd mathematical bugs, signaling the need for a deeper revolution in how we conceptualize gravity. M-theory stands as the leading theory of everything. Central to M-theory is the idea that our perceived 3D universe exists on a membrane, or brane, which itself floats within a higher dimensional bulk volume. Experimental clues for these extra dimensions predicted by M-theory could emerge from the LHC's work. One way is through precision measurements during collisions to detect any deviations in the gravitational force between particles at very small distances. Measuring minuscule enhancements in gravity at subatomic scales could flag gravitational interactions with the additional spatial dimensions required by M-theory models. M-theory allows for the fleeting formation of microscopic membranes, orbifolds, or other exotic structures when energetic particles collide. Detecting traces of such objects would provide smoking gun evidence for M-theory and extra dimensions. Cern scientists anticipate finding new unknown particles not included in the standard model, like superpartners, Kaluza-Klein excitations, or axions. These new particles are ingredients specifically predicted by M-theory. The future experiments at LHC are planned to further research on the missing links between the M-theory and theory of everything, as they are expected to reveal much about our past, present, and future. As Stephen Hawking said, "A complete, consistent, unified theory is only the first step. Our goal is a complete understanding of the events around us and of our own existence." The LHC's ongoing work may uncover experimental evidence supporting M-theory's vision and extra dimensions, moving physics closer to the unified understanding Hawking described. Number 11. Destroyer of the universe. When the Large Hadron Collider neared completion, fears spread through some media quarters that its unprecedented high-energy collisions could potentially spawn an uncontrollable black hole that would consume Earth or trigger a cataclysmic chain reaction, obliterating the universe. The basis for these conjectures was that concentrated bursts of energy from LHC proton collisions could theoretically convert into enough mass to form microscopic black holes. There were concerns these black holes could then grow uncontrollably through runaway accretion, eventually engulfing Earth itself. Others worried such black holes could trigger a chain reaction distorting the fabric of space-time and destroying the known universe. However, the scientists at Cern firmly repudiated these doomsday scenarios as impossible. Natural cosmic ray collisions occur at energies exceeding the LHC routinely in Earth's upper atmosphere with no adverse effects. Calculations also definitively ruled out any black hole produced by the LHC growing uncontrollably. Quantum effects cause such microscopic black holes to rapidly evaporate away harmlessly in a flash of Hawking radiation. Number 10. Ultra-high-energy cosmic ray collisions. Ultra-high-energy cosmic rays have been colliding with particles in Earth's upper atmosphere for billions of years, long before any human-made accelerator. These cosmic ray collisions reach energies millions of times greater than even the Large Hadron Collider can currently produce. Surprisingly, studies of these naturally occurring cosmic events provide clues related to one of the LHC's key interests, searching for evidence of extraspatial dimensions beyond the 3 dimensions of everyday experience. Certain cosmic ray collisions with energies exceeding 100 billion electron volts produce extensive air showers containing hundreds of muons in the resulting particle debris. However, theoretical models predict the number of muons generated should be even higher based on the immense energies involved. This muon deficit suggests that a sizable portion of the energy in these ultra-high energy cosmic ray events is not accounted for in the observed outcome. One explanation proposed by theorists is that fleeting microscopic black holes may momentarily form during the most energetic cosmic ray collisions. As predicted by quantum gravity theories, these transient black holes could provide a temporary gateway to additional curled-up spatial dimensions outside our normal 3D reality. Energy gets briefly transferred into these extra dimensions and thus cannot be detected from our limited perspective, making it seem missing. The muon deficit signature seen could therefore provide indirect evidence that cosmic ray collisions involve quantum gravity effects and access to the extra dimensions hypothesized. Number 9. Quantum entanglement and teleportation. Research at Cern goes beyond probing extra dimensions. The Large Hadron Collider is also being used to test a fundamental quantum phenomenon: entanglement. Entanglement occurs when particle states remain mysteriously interconnected, regardless of space and time separation. Extension of entanglement knowledge gained with the LHC could potentially even aid goals like quantum teleportation. Quantum entanglement has usually been demonstrated in labs over kilometers using photons. However, by producing entangled pairs of massive particles like protons through LHC collision events, scientists are trying to probe quantum effects at macroscopic scales and matter densities closer to everyday experience. Observing any deviation in entanglement behavior compared to established quantum theory would signal exciting new physics possibly tied to hidden dimensions. Number 8. Time travel potential. Within the first second after the Big Bang, the four fundamental forces of nature took shape. Matter transformed from a hot, dense soup of quarks and gluons into the first protons and nuclei. By recreating these fleeting conditions, the Large Hadron Collider provides a bridge to revealing secrets from the cosmic dawn of creation. In this sense, the ultra-high energy collisions achieved within the LHC serve as a kind of time machine back to the early universe. Within its experiments, the LHC momentarily reaches temperatures of trillions of degrees and matter densities not seen naturally since the Big Bang itself. This exotic state of quark-gluon plasma last existed freely in the instants after the universe formed, before quarks and gluons quickly condensed into more complex particles. By investigating this remarkable transient form of matter, physicists gain insights into the intense, strong nuclear force that binds together protons and neutrons. Additionally, the particle content and interactions in the brief moments after the Big Bang depended on physics operating at extraordinarily high energies, currently far beyond the reach of any achievable collider on Earth. However, by pushing to the extremes possible, the LHC data provides the best clues available today to piece together the nature of physical laws just after the genesis of space and time. Cern's time machine represents perhaps the best hope of unraveling the enigmas of cosmic existence by experimentally rewinding the clock on the universe. Number 7. Testing multiverse theories. In recent decades, the theory that our vast universe exists alongside an infinite multiverse of alternate parallel realities has gained more widespread consideration. While impossible to directly observe, precision measurements achievable at the Large Hadron Collider could provide clues or hints about this captivating possibility. Within hypothetical cosmological models, an infinite array of separate universe bubbles can exist, each with differing versions of reality exhibiting alternate fundamental physical parameters, particles, and laws. Subtle signatures of this may come from tiny variations in physics phenomena that the LHC is uniquely sensitive enough to probe all the way down to the smallest quantum scales. For instance, detecting minuscule changes in the measured strengths of forces like electromagnetism across experiments or slight deviations in observed masses of particles could hint that our universe represents just one possibility selected from a landscape of many with differing cosmic settings or constants. Additionally, effects related to symmetry violations like CP violation could show up having subtly different characteristics between measurements. Such small variations could reflect our universe being fine-tuned, with one specific set of fixed parameters distinguishing it from the multitude of other universes possible where constants differ. Number 6. Artificial black hole. One vision occasionally discussed within the physics community is whether the Large Hadron Collider could be used to create a well-controlled artificial micro-black hole safely within the confines of its detectors. While seemingly fanciful or speculative, this could open up an entirely new window into understanding gravity, extra dimensions, quantum effects, and the nature of space-time itself. The immense collision energies achieved at the LHC allow concentrating enough power into a sufficiently minuscule space that micro-black hole formation could be possible, at least in principle, based on Einstein's famous mass-energy equivalence. However, there are major caveats to the current reality matching this visionary goal. First, baseline LHC collision energies are likely still below the threshold required to produce even a small black hole, despite already representing the highest energy particle collisions achieved. Significant future planned upgrades would be needed to continue pushing this boundary. Additionally, there are complicating effects like the composite nature of protons that make clean black hole production difficult. However, if these challenges can be overcome, safely creating a minuscule black hole could potentially allow unprecedented insights and discoveries. Measuring the decay of a black hole through emitting Hawking radiation, for instance, would prove this elusive phenomenon exists. Furthermore, if theories involving extra dimensions hold true, black holes produced could reveal a deeper understanding of gravity and its behavior in higher dimensional spaces. Now it's time for today's subscriber pick. According to quantum physics, our universe exists among many alternate dimensions vibrating at different frequencies. Generating intense energies can cause ripples and distortions in the fabric of space-time by creating microscopic black holes or warping additional spatial dimensions, briefly allowing contact with a parallel dimension. When Cern recently powered up the Large Hadron Collider, trillions of protons collided at extreme energies. According to some reports, this extreme velocity momentarily distorted physics, disrupting energy and weather patterns worldwide as our universe made brief contact with another dimension. The intense quantum interactions created by the LHC may have caused unanticipated ripples in space-time. What do you think? Could experiments like this lead to unexpected distortions of the fabric of the universe? Let us know your theories in the comments below. Number 5. Strangelets. Within the particle zoo of known and predicted subatomic particles, so-called strange quarks stand out as an unusual breed due to their significantly greater mass compared to up and down quarks, which make up ordinary matter. Some speculative theories propose that strange quarks could combine into hypothetical strangelets with unexpected properties at the high energies inside the Large Hadron Collider. However, extensive research has concluded that LHC experiments pose no conceivable threat through uncontrolled strangelet production. Strangelets would represent a form of strange matter, made up of a high concentration of strange quarks stabilized by a strong nuclear force. Some conjecture that if produced, strangelets could convert normal atoms they contact into more strange matter through a runaway process. Studies show several factors prevent strangelets from being produced in significant numbers at the LHC if they form at all. The enormous energies required make them overwhelmingly unlikely to appear. The fleeting microseconds of LHC collisions also provide insufficient time for conversion reactions to occur. Independent experts have definitively concluded that there is no risk of strangelets spawned at the LHC triggering a disastrous chain reaction. Number 4. Plasma wake field acceleration. In scenarios far different from its particle collision explorations, research activity related to the Large Hadron Collider has also provided valuable contributions to developing the futuristic concept of plasma wake field particle acceleration. This technique uses waves in plasma to accelerate particles to high energies over much shorter distances than existing methods. Realizing this could enable a new generation of smaller, more powerful particle accelerators. LHC physicists proposed using a proton fraction to induce plasma wake fields, accelerating electrons rapidly. Experiments validated accelerating gradients thousands of times stronger than current methods. Though early stage, this could transform technology, making tabletop LHC-level colliders feasible. Also, the extreme conditions created in the LHC have given glimpses of matter as it existed mere microseconds after the Big Bang. By colliding lead nuclei at near-light speeds, physicists have created tiny droplets of quark-gluon plasma, the densest matter in our universe outside of black holes, a state of matter so hot and dense that quarks are no longer confined within individual protons and neutrons. Like the first moments after cosmic creation, exotic primordial particles emerge freely in this fleeting quark soup before cooling rapidly back into familiar atomic matter. The LHC furnishes a brief window into the infant universe when particles flowed freely moments before stars and galaxies formed. Number 3. Antimatter breakthroughs. Experiments at the Large Hadron Collider have furthered our understanding of antimatter, advancing capabilities to precisely study its properties. Precision measurements of antihydrogen atoms formed at Cern's antiproton decelerator reveal clues about fundamental symmetries between matter and antimatter. Improved antimatter research aids in understanding cosmic mysteries, like why the observable universe contains virtually no antimatter. Antihydrogen atoms consist of a positron orbiting an antiproton nucleus. Cern instruments isolate samples of antihydrogen within electromagnetic traps and turn off the fields to allow the antimatter to be probed for tiny differences compared to normal hydrogen. In 2021, an enhanced measurement of antihydrogen's atomic spectrum showed no deviation at a precision of 2 parts per billion compared to hydrogen. This narrows the window for any possible asymmetry between matter and antimatter that could explain why matter prevailed in our universe after the Big Bang. Additionally, a new measurement determined antihydrogen is attracted by gravity at the same rate as normal matter to a precision of 1%. Finding any difference could overhaul theories of gravity and antimatter. While no radical divergences have been found yet, these stringent empirical constraints guide cosmic models and the quest for a more perfect symmetry between particles and antiparticles. Number 2. God particle. The Higgs boson gained widespread fame following its detection at the Large Hadron Collider in 2012, with some media outlets even sensationally labeling it the God particle. However, many scientists express disdain for this controversial epithet, which overhypes and misrepresents the nature of the fundamental particle. The problematic moniker arose from the title of physicist Leon Lederman's 1993 book on the history of particle physics, The God Particle. If the universe is the answer, what is the question? He intended it as a metaphorical reference to the pivotal role and elusive nature of the then hypothetical Higgs boson, rather than literally implying it had religious connotations. However, taken out of context, marketing gravitas led God particle to become an oft-repeated misnomer. In reality, the Higgs boson is simply an ingredient in the prevailing standard model rather than some divine creator. Nobel laureate Leon Lederman himself lamented the distracting nickname, admitting he never should have kept his original working title. Number 1. Future LHC upgrades. The LHC Run 3 started on July 5, 2022, after over 3 years of upgrades and maintenance. The LHC is now operating at a record energy level of 13.6 tera-electron volts, allowing for greater precision and discovery potential than ever before. The LHC experiments have undergone major detector and data system upgrades to collect significantly larger, higher-quality datasets. The ATLAS and CMS experiments expect to record more collisions during Run 3 than the previous 2 runs combined. But Cern has even bigger plans in store. Future upgrades aim to further expand the cosmic frontiers that groundbreaking instruments like the LHC explore. Planned upgrades will increase the luminosity of proton beam collisions, resulting in more collision events per second. After the current round of upgrades, luminosity is expected to increase by a factor of 2 to 3, providing more data to potentially uncover rarer phenomena. Looking further ahead, the high-luminosity LHC project will employ cutting-edge technologies like more powerful superconducting magnets and enhanced detectors to achieve an extraordinary 10-fold increase in luminosity compared to the initial LHC. This luminosity-pushing phase is slated to begin operations in 2029. Additionally, investigations are underway regarding even more ambitious future circular colliders that could reach spectacular collision energies of 100 tera-electron volts, nearly 7 times greater than the current LHC. New technologies will be required to realize this vision in the coming decades. Thanks for watching, and we'll see you in the next one.